All right, we're on the hour. Thank you, everyone, for attending our webinar here. Excited to get our webinar will be focused on dynamic stability models, dynamic models, and studies for interconnections. So just a little housekeeping as we get started here. You'll note here on the slide, marketing at cai-engr.com for those looking for PDH credits for attending today's webinar. Please reach out and we will provide those credits to you. Also note that as we go through the presentation, feel free to post questions in the chat. We will address questions at the end of the presentation in a Q&A session. Also, during the Q&A session, you can also post questions. Note that we will do our best to get through all questions throughout the hour, but we will end promptly at 1 o'clock Eastern. Any additional questions that we don't get to, we will reach out to you individually if you post your contact information as well. Excuse me, if you just post your question, we'll have your contact information. We can reach out to you after the presentation if we don't get to your question. We want to make sure we give a chance for everyone to address them. Also, just a heads up, this is part of our series. We've been having monthly webinars on power systems topics. I hope everyone's enjoyed them so far. We will be presenting another one in January to be posted after the holidays, beginning of the month. So look for that invite in early January for our next one. So just a couple quick introductions. Myself, I am Ian Hutt. I lead our system studies team here at Commonwealth. I have 2 degrees from Central Michigan University. I've been doing studies for my whole career, pretty much 20 years here in the power industry and studies as well. Licensed in a multitude of states across the country. Also presenting today will be Chris Nelson. Chris Nelson's also from Central Michigan University, Fire Up Chips. 15 years working in power system studies and in the industry, in the power industry himself, licensed in Michigan, and he is our subject matter expert in transmission planning and interconnection studies at Commonwealth. So we're going to start with a question. We're going to have a poll that'll pop up for you here. So just kind of a quick question to gauge your experience with dynamic stability and dynamic stability models. So look for that poll to hit and then please answer, and we'll continue here once we have the poll closed. Oh, I think this is the wrong poll, Dell.
Oh, my apologies.
Oh, no problem.
Could we come back to this one, do the next slide, and we'll come back to this one in just a moment, if you'd like.
Yeah, okay, we'll give you a minute here.
Thank
we'll
you.
come back. Sorry that we'll answer that. We'll have that question a little bit later. So I'll cover the agenda while we're pulling our poll up. So the agenda today, we're going to talk about what is a dynamic model. We're going to talk about the input and information required to develop a dynamic stability model. Types of dynamic studies that tend to be done with these models, and what the utilities and I guess it doesn't have to be utilities, but any of our customers would like to do with these studies. We're going to talk a little bit about utility and ISO requirements. This is going to be kind of a hot topic. We're seeing these dynamic models being required for most interconnections, both on the large load side and on the generation side, both conventional and renewable. And we'll also talk about some general tips. So when we're talking about putting together our generation interconnection agreement or large load interconnection agreement, just some things that are helpful to understand, some parts and pieces that can make that process go a little bit smoother. And then we'll open it up for QA here at the end. So Dell, if we have that poll up, Chris, do you want to go back a slide?
One moment. Here we go.
Hey, we're up. So if you want to take a moment here, we're just kind of looking to gauge the audience to see what your expertise and experience is with dynamic models so far. So if you don't mind, please answer the poll, and then we'll continue from there. Give it just a moment here as the responses come in. I appreciate everyone's promptness here. All right, we're in at 29 responses. 30 is the last couple come in. So it looks like overwhelming majority are here to learn and don't have any experience with dynamic models yet. So we'll keep that in mind as we continue through our presentation. And hopefully any questions we have, we'll be able to address that way. Chris, I think you stopped sharing your presentation.
Did it stop?
Yeah, it stopped. We lost it.
Let me fix that then. Try this again. All better?
Yep, we're all set. All right,
Okay,
with
sorry
that,
about that.
Chris, I'll hand it over to you and take it away.
To start with, I wanted to just kind of go over what dynamic stability is, what it looks like when things are good, what it looks like when they're bad, just kind of high level overview of it. So it examines the instantaneous response of usually a generator, but also loads can be modeled. And if there's a fault or some sort of disturbance in the system, they should respond in a certain way. Usually there'll be like a blip on the graph of what the generator is doing, and then it'll settle back down to its new normal. But if it's not behaving, it might go a little haywire. Most utilities do require for interconnection, they require a site-wide study, which they use to create a wide area study. And it just evaluates the dynamic response of a wide area one. Will look at multiple faults across the system and see how just the system as a whole behaves. So just to start with, the first thing you would do after you create a model is you would graph the voltage or the frequency or various parameters and see how it behaves without a fault in the system. Because if the voltage is fluctuating when there's no fault in the system, there's probably a problem with the actual model. So usually we'll model voltage, frequency, megawatts, megavars. Sometimes if there's a fault, it's normal for it to oscillate, but like I said, it needs to settle back down. Some utilities have specific limits for what that looks like. Some utilities are more, it looks good, it's probably good. It really depends on what the utility is, but I guess the main point I wanted to make here is that they call it running flat. It needs to, if there's no problem with the system, the voltage needs to be a flat line and preferably near 1 per unit too. So this is an example of a voltage disturbance on the system, and this isn't so much a fault. This is a small site with the utility, the point of interconnection running a little higher. So the point of interconnection is set to 102% of nominal voltage for the duration of the test. And you can see that's the blue line in this graph. So it goes a little bit higher and then it settles back down to 102% and it just stays there. And the red line is the generator that's a couple transformers deep into the site. It spikes to 102 and then it tries to fix it. And that's what it should do. It needs to try to fix the voltage. It's not going to be able to affect the utility much because the utility is so much bigger, but it has to try. And if enough generators behave the right way, then the utility will go back where it should. And the way it actually does this, it doesn't have like a voltage control so much as it injects VARs or subtracts VARs from the system, and that affects the voltage. So this is an over voltage case, so the generator runs with negative VARs to lower the voltage is basically how it affects that. The next slide, we're talking about a frequency deviation. The point of interconnection is running a 0.5% lower frequency. I think I don't remember exactly what the math is. I think it's about 59 2/3 hertz. It's pretty close. It's not a very large voltage or frequency disturbance, but both the frequency of the POI and the generator are dropped down to that same one. and the generator tries to fix the frequency by pumping out more megawatts. In this case, it does real power instead of reactive power to try to fix it. I think this might have been an inverter, but it basically tries to mimic speeding up an actual, like a regular generator to fix the frequency. This might have actually been a conventional generator. I don't remember this particular one. So we have another question. If you wanted to put the poll out, Dal.
Yep, sounds good. So for this question, we're just kind of testing knowledge a little bit. No wrong answers. We're just kind of trying to get gauge for what people think based on where we are so far. So what is the main indicator of a stable system based on what we've talked about? So you can put your answers in the chat and we'll respond here in just a moment. All right, as the answers are coming in, it looks like we're the majority of our answers are reactive power response to a change in voltage. Chris, what do you think about that?
I think that's exactly correct. It needs to pump out a few more VARs to raise the voltage or negative VARs to lower it.
All right.
So what is a dynamic model? To start with, we have a steady state power flow model, usually in PSSE or PSLF or some other programs. But a dynamic model builds on that and creates basically generator parameters. It's for a conventional generator, it'll usually have generator parameters that you can use to create the dynamic model file. If it's an inverter-based generator, that information is usually, I don't know if it's proprietary, but it pretty much has to come from the inverter manufacturer. So they'll give you a dynamic file with all the dynamics in it, and you pair that with a power flow model of the site. Typically, PSSE, PSLF, or TSAT are the programs we've seen you do this, but there are others less popular. PSSE tends to be more popular in the east side of the US, PSLF in the west. TSAT's kind of up and coming, but it's getting popular, I think, everywhere. So to create a model, some of the information you need just for a single generator site. This is, for example, just a single conventional generator. Might be a large generator, might be a small one, but you'll need the cable schedule for all the cabling from the generator to the point of interconnection. You need transformer specification, and the more detail you have, the better. We can usually make estimations of that, but if you have the actual, like a transformer test report, the better data you have, the better output you'll have. You'll definitely need the generator nameplate information, and usually you'll want a D curve for that too, so you know exactly how much reactive power it can put out. And then you need to either have or create a dynamic file, and that'll be usually a DYR or DYD file. And like I said, for a spinning conventional generator, usually you can create that with the parameters of the generator. But for the inverter, you really need to get that from the manufacturer. There's not a way to create it. So,
all right, we're going to question here. So we talked about some of the software that is available for doing the dynamics stability studies and what's required by the utilities. Which one do you think is the most popular? All right, poll should be up, so we'll wait for your votes here. Responses are coming in. Get a number of responses. So we are overwhelmingly showing PSSE. What do you think, Chris?
I think that's probably true, but we might be a little bit biased because we're situated in the east and we work more on the east side, the East Coast than we do the west, but we've seen PSLF too. I think both are pretty popular. I think PSSE is probably more popular though.
One thing I'll mention too before we move on is I noticed there's a number of responses that look at PSCAD. So PSCAD is a heavily detailed transient program, very powerful tool. And we do have a lot of studies that we tend to use that tool for. Specifically, we'll look at things like harmonics. We'll look at temporary and transient overvoltage. We'll do a look at switching studies and things of that nature with that PSCAD model. However, the PSCAD model, because of its intense and high level of detail, it's very difficult to look at things in a system-wide level. That's where the PSSE and PSLF tools tend to excel, and TSAT, as TSAT gains some more popularity and more requirements across some of the ISO communities and areas and regions. So I don't think that the answer here is wrong. I think you can absolutely do some dynamic analysis with PSCAD, but it is much more time intensive, I think. So just one thing to kind of know as we look at some of these results.
Yeah, I think some utilities do require the PSCAD model specifically to look at the dynamics, but like you said, they probably don't run it on a site or a wide area. They only look at that site to make sure it works.
Yeah. Yeah, I think for a local analysis, it's maybe the right tool.
Yeah. So we talked about a single generator. For a single generator, it's somewhat complicated, but it gets a lot more complex when you have multiple generators because most utilities don't, actually, I think every utility, they don't want you to model all your generators. There's too many bus numbers. It makes everything run slower and worse. So they usually want a single generator, a single cable, a single transformer, and that's your whole site in their model. If you have, for example, a solar and a battery, you might have two different generators, one for each, but they want you to combine into as small of equivalent as you can. For if you have, let's say, five megawatt generators, you can add a 5 or a 25 megawatt generator and a 25 or 30 or whatever the transformer is, megawatt transformer or MVA. But the cables get a lot more complicated. Because a lot of the time they're daisy chained, a lot of the time they're not. The cables are different sizes. You can't just add the impedance up. There's some pretty complex math that goes into that. And that was actually what I was going to talk about here. So I guess I covered some of this slide already. But in the example on the right, there's 4 generators. Z1 is the impedance of the one cable that feeds generator 1, and that one's simple, but Z2 feeds both generators 1 and 2, and Z4 feeds all 4. So you almost have to count the impedance of Z4 multiple times if you're doing it. I'm not going to go over the math in detail, but there's a guide that we've looked at. There's actually a couple of guides. I think the WEC guide makes it a little easier to understand, but it seems like the guide that everybody references is the methods of equivalencing a large wind power plant with multiple turbine representation. You can look that up if you're really curious about the math, but it takes a bit to understand.
All right, so moving into question here. So quite often when we're dealing with stability models, rather than calling out a model or calling out the software in which the model is developed in, they'll call out a file extension type. So we've got a number of file formats here that were listed in our poll. Take a quick look. And if you want to put your vote in, which one do you think is the typical file format used for dynamic studies? Wait for the poll to conclude here. All right, we are. It looks like we have almost everybody here coming in with a DYR file. So I believe that is correct. So when it comes to the PSSE software and the PSLF software, both, they're dynamic file type is this DYR. You're finding it also as we go through industry nomenclature. So when someone asks, okay, provide your DYR file, what they really are trying to tell you is we really need a stability model for your application or your project. And this is the file format that they expect that to be in. So that .dyr has kind of become a synonym for a dynamic stability model.
I think PSLF uses the DYD model actually, but I've heard a lot of people call it the DYR file because it's just the term everyone uses. This was also a little bit of a trick question too, because the save or the raw file or the EPC file, if it's PSLF, are the start of a dynamic model. It's just that the dynamic information is in that DYR file. It takes both the steady state and the dynamic information to create a dynamic model. So none of the answers were technically wrong.
Yeah, absolutely. So when you're looking to submit your dynamic stability model for your application, for your project, it's not enough just to give them the DYR. You really need both. You need to have the .save file or the .raw file. It can be either or. There are two different file save types out of PSSE for their steady state models. And then that DYR, the dynamic stability, is something that runs on top of that. All right, thank you.
So we've also seen, it's not just generators, we've seen data centers that need dynamic modeling. There's some simple dynamic modeling for loads, but most utilities that want the complex modeling, and it's a little bit more of a task to create that complex modeling for one of these than it is for a generator. But we've seen a shift where it's not just or not just data centers, but any large load, which is usually a data center, they are requiring dynamic load models in a lot of places. New York ISO is one that we personally worked on, but I know I've seen a guide where MISO, they explain in detail how to create this. It was a pretty detailed guide and it was pretty useful actually. I don't think New York ISO had a guide, so I watched the MISO guide to see how they did it, and it was a good resource. So what is a dynamic study used for? Utilities, they'll require a single system model for interconnection, but when they get that model, they'll create a larger model from it. But they also, for their larger model to work properly, they need the single site model to be modeled correctly, and there's a shift to use a lot more quality control in that. So you can create a model and just submit it without any testing, but it may or may not work if you don't test it. And they're requiring a lot more testing than they used to. We do recommend doing at least some minimal testing, even if it's not required by the utility. We've shifted so that we test all our models for, and any software we use, we do at least some minimal testing to make sure it behaves right. Because we just don't want the utility to come back and say we need to fix the model if we could have done it in the first place.
Yeah, it's kind of critical too. I mean, making sure that this can be a time sink, right? So some of these models, they'll be submitted and maybe not reviewed for months and months. And if there's problems with these models, it can be a potential schedule impact of your project. So I think that's an extra consideration, is to make sure that even if there isn't required testing as part of the ISO standard, that these models are tested and proved to be in working order. So when eventually these models get reviewed, and maybe it's months down the road, that there's not a potential schedule impact for your project. Moving to the next question. So I guess that kind of elaborates on the same topic we're just talking about. So so do we think that dynamic models need testing? So what do we think? Polls up. All right, we're coming in pretty heavy on yes. A couple people would no. So I guess testing does drive up cost. So there may be a consideration for that. I will say that just based on our experience, we've had to put together and test a fair number of these models here, especially in recent times. This has been a new standard that's been pushed across the country and across the industry, that we heavily recommend doing some testing to at least make sure that it's functional before it goes out.
Yeah, I guess technically the answer is it depends on the utility, and a lot of them don't require it. But from what we've seen, we'll get a DYR file from an inverter manufacturer, or we'll have a conventional generator and we'll create one and we'll model it, and they just don't always behave at the start. We'll have to do some tuning and maybe change a parameter, and that might even mean that they have to change some parameters, like in the excitement of the generator. Sometimes we actually have to tell them to run their stuff a little bit differently for the dynamics to work, and that affects the real machine and not just the model. So sometimes it's a pain to track down what's causing it, but that just comes with experience, I think. And part of testing it is tracking down why it's not working and trying to fix it, and it may or may not be easy. So we do recommend it because we've definitely seen a lot of models that don't work right off the bat.
Yeah, a good point too is a lot of these models, when we get them, they may be coming in from the manufacturer, the vendors, and it's definitely not all models are equal. So certain manufacturers and vendors have much cleaner, better running models that we can start with and then use to pull together an aggregate site model. Whether it's one inverter or 500, and we would use those models from the vendor to help build that full site out, whether we go with an aggregate version or a detailed version. But you're right. I mean, some models are broken, and if it's bad data in, it's bad data out. So we need to find a way to get through those challenges and identify them early to understand what the overall impacts are going to be.
So once the utilities get a model from you, and most of them, maybe all of them, but most of them are requiring some sort of model at this point for generation. And we're seeing mostly transmission level generation. I'm not really sure what the landscape looks like if you're connecting to distribution. Do you know more about that, Ian? Have you worked with that?
Yeah, a little bit. So it kind of varies by utility, like you said. So for distribution level interconnections that are non-BES, so it depends on your region. They may be 74.9 megawatts, just under the threshold. They may be different regions like ERCOT and say CAISO is going to have different requirements for whether distribution has to have modeling. I think it's going that way where the requirements are getting more and more challenging to meet. These requirements for models are changing on a month-by-month basis, and we're seeing that it's definitely trending to the way where these models are being required for almost all products. There's going to be some minimum thresholds for small commercial, small residential that wouldn't apply, but for any kind of mid-sized, even distribution connected commercial project, you're seeing that on the generation side and on large loads as we move into this new world with the data center boom that we've seen so far.
Yeah, it seems like there's just such a glut of solar, mostly solar, but batteries and just general. There's a lot more generation in the interconnection queue than there ever was in the past. It almost seems like they're trying to pick and choose the best ones, and they're weeding out a lot of them that don't have. A lot of it's just paperwork and getting the modeling done, but they're requiring just a lot more to get anything built. And the reason they need this, usually it's not always on the utility. So the utility will collect a site dynamic file and they'll create their system-wide model, but they have to submit their model to MISO, and it has to be, everything goes up the chain a little bit. So MISO has their entire model that's all of MISO that runs, and I've seen it, and it takes a minute to run, but it works. And they check their whole system once they get all the data from all these little sites. And like I said, that's what they do with it. They splice together a bunch of little models to create their larger model. And then they do a wide area dynamic study. And what that looks like, it's usually, they'll have a wide area model, but they don't necessarily run faults on the entire model at once because that would take days or weeks to run. They'll probably run an area of interest that they're looking at. Like they'll have the entire model, they'll have the entire interconnection of MISO mapped out in the model. but they'll only run faults near a newly connected generator just to make sure that generator works. Because even if the generator works on a small site, it might not behave perfectly in the larger model. So that's what they want to run and find out. Just to make sure all the generators behave together instead of just by themselves. And they will want to make sure the whole system is stable. And if you have an unstable system, let's say you have 20% of your generators are not modeled well, it's really hard to get that flat run to begin with, so you can actually see what's wrong. If it doesn't run, like if the voltage profile is bouncing back and forth without any disturbance, it's hard to really tell what the cause is when you put a fault on the system. So it's important to have the full system be stable and not just the one generator. And we've worked with utilities where their model was not very good, and it takes a lot more work to try to clean up and make work. The reason that utilities do this is because the models, they're not just for modeling, they're actually showing you what could happen in real life. If enough generators fall out of sync, you could have a full collapse of at least an area of the grid, and nobody wants that. I think we've heard about that in 2008, maybe 2003. People tend to get fired over that. So people are pretty worried about that. Even just a couple of generators that are not behaving right to a fault, they can lead to pockets of the grid just falling out of sync and just well, maybe longer durations, but short or smaller area of outages. And our goal is to identify these problems before they can actually happen. I guess the biggest point we're trying to make here is that there's a major shift towards a lot more detailed modeling. Most of this is because there's a shift towards renewable energy. There's a lot more smaller generators replacing all the larger generators we used to have, or they're running. The larger ones are still there, but they're not running because there's solar power running all day. Either way, there's not really any spinning mass in there's just not enough inertia behind the power that inverters provide. So a conventional generator might provide 8 to 10 times the fault current of nominal if there's a problem, and it'll just continue spinning even if there is a little problem. Inverters might not do that. They just don't have the inertia behind them. And we've seen problems with relay settings as well, but they're doing the best they can to work around that. Either way, utilities are requiring a lot more accurate and detailed models to try to make sense of what's going on and make sure that the grid is as stable as they can make it. Another thing a lot of utilities and ISOs are doing is requiring PSCAD models specifically for inverter-based resources for solar or battery. Probably wind as well, but if you have an inverter-based generation, it's likely they're going to make you submit a PSCAD model alongside your regular dynamic model. I know ERCOT and MISO are definitely doing that. I think a lot of other utilities are following suit.
All right, moving into our next question. So just kind of gauging the crowd here for maybe ways that this topic has affected you. So just checking to see if anybody is working on projects that work in these renewable areas. And if you're working in multiple, maybe pick the one that you've done most recently. I don't know. Seems like a reasonable thing. All right, we have a lot of responses. So it seems like most people here, even though they don't know from the first poll, we don't have a lot of gauge on experience with dynamic models. It seems like we're working in a lot of projects where this is going to be something that affects you. So I'm really glad that you're able to attend, and hopefully you found something valuable from this discussion. Yeah, it seems like we're almost 80% or a little over 80% have been working in renewables.
Yeah. So just to cover some of the specific utilities we've worked with and seen, one of the strictest ones we've actually worked with is ERCOT. They have, probably because they're a smaller grid and they have to have more quality control just to make sure they function. They have a lot more strict requirements for model quality and just model testing than anybody else we've seen. They have a specific form you have to fill out. There'll be, you have to run different faults on the site depending on if it's an inverter or conventional generation, but they have very specific tests you have to do. Like they'll say you have to run the point of interconnection at this voltage or this frequency and see what your generator does. And if it doesn't go to this exact level, it fails the test. So they have very laid out tests on what needs to be done. So they'll look at that flat run. They'll look at the large voltage disturbance, which is just another term for a fault. It'll usually be 3, maybe 5 cycle fault at the POI. They'll look at voltage up and voltage down scenarios, and then they'll look at frequency up and down scenarios. And actually for the frequency, I believe for the frequency, they want you to modify the steady state case so that the generator is only putting out 80% of its power. So it has a little bit more headroom. Because going back about 10 slides, we talked about how, the response to a frequency up or down is active power. So there has to be headroom for the generator to put out more power if you're going to lower the frequency for it to try to fix it. So that's one of the tests they do. For inverter-based resources, there's probably about double that many things they do. They have a lot more like ride-through requirements and things like that. And they have a lot of very specific tests at ERCOT. I think they need their steady state model to be pretty detailed too. I think ERCOT is one of the ones that's requiring a PSCAD model for inverter-based resources too. It might be only specific ones. I don't think we had to do that. No, I take that back. I think it is all inverter-based resources, but it was a conventional generator we worked with on ERCOT. And in our backyard, MISO is kind of trending towards the same thing. As far as I can tell, their current guides on how to do all their studies don't mention any of this, but all their draft guides for the past 6 months or so have been asking for a lot more model testing, and even some projects that are in flight that didn't have these requirements when they were started. I think MISO is requiring them now. That might be a little bit of a gray area for the lawyers to figure out, but they're definitely trying to require it. And they're looking for very similar to what ERCOT was. They want all those same tests run, maybe different parameters to prove that it's good and bad, but they're very similar. And they're looking at, I think they are running both PSSE and TSAT models, but I don't think that'll be a long-term solution. I think they're switching to TSAT entirely. They just haven't quite phased out PSSE yet. So actually, right now, I think for certain types of generation, they want PSSE and TSAT models. So you have to do double the work. But I think they're going to transition to just TSAT in the future. And we've worked on a lot of interconnection applications over the last couple of years. And like I said, we've seen a lot more renewables coming in. Just a lot of battery sites, a lot of solar sites, a lot of combined sites. Some of the things you can do to try to make the process go better is just to make sure your data is as clean as you can to create the model. If you have to, if the model fails whatever test the utility has and you have to fix it, it's not just the time it takes to fix it. It could slow your whole project down because late in the game, they might decide you can't build it until you fix this. So if you're under construction, that could cost a lot of money to pause the construction just to finish this, or to finish the construction and not let it go online until it's done. Getting the latest requirements from the utility you're working with is also very important because, especially with somebody like MISO, they could be changing it in the middle and you have to follow what they tell you, not necessarily what they did a year ago. So if they're requiring a PSCAD model, you need to know that and probably budget for it and plan for it for time. And it can be a problem if you don't expect it. And as you design the site and get it a little bit more fleshed out, you'll need to update the models. The dynamic model could change, especially if you change inverters or large equipment gets changed. It's just something you have to update as it goes along. And most utilities will have a process for when they check things like that. Did you have any other tips, Ian? Guess not. We might have lost Ian.
Oh, sorry, guys. Sorry, guys, Chris. I had a small internet hiccup. What was that
Okay.
question?
I was just wondering if you had any other tips we could talk about on this.
Yeah, I think getting started early is important. So when it comes to these models, they take time to develop. So, depending on the complexity, some of these models may take between 2 and 6 weeks to put together, especially if we're required to build a from scratch dynamic file where we don't have vendor input. And like Chris mentioned earlier in the presentation, it may be possible or not, depending on what type of generator we're talking about. With a lot of the inverters, the manufacturers of the inverters themselves provide the DYR files. So that's a starting point. Their inverter DYR is not enough to satisfy the utility whole site requirements. So we would take those models and put them together to build the appropriate model. But just like we talked about earlier, poor quality inputs can be problematic. Sometimes working with the vendors can be challenging and difficult, especially if they're not US based or don't have a US based engineering arm to support you. So again, my advice is start early, understand your technology. If your technology changes, understand that there may be impacts to this. This could be something that may potentially even have schedule impacts for your project. So for example, you change vendors of inverters because of pricing or capability or availability. That may be that this can affect this model, this process, and potentially be a slowdown point for your project.
Yeah, we've definitely worked with inverter manufacturers and other manufacturers that you might get the data from them, but it's going to be a lot of back and forth, and it might be a month before you even start to get anything from them. Just depends on who you're working with.
I agree.
We probably don't need to call out names on who's no good at that here, but we've definitely dealt with both sides of that.
Yeah, but not all models are equal, that's for sure.
Yeah.
All right, with that, appreciate that discussion, Chris. A lot of good information. We will open up the Q&A. So what I recommend is if you have a question for us, please post it in the chat and we'll walk through your questions and try to provide as best answers we can. While we're waiting for questions to come in, yeah, maybe just some other things that we can talk about. So we talked about the different software that we're using. We're using PSSE, we're using TSAT, we're using PSLF. So just kind of a reminder, when it comes to PSLF, that generally is more popular in the West Coast. That's something that kind of affects California projects. We're seeing it in traditional power markets in the West as well. It tends to be the flavor that they prefer. However, there's conversion between those products, which is nice. So for example, say you had a requirement for a PSLF model, but maybe you don't have that software, and the software is prohibitively expensive. Getting your license is pretty substantial. I can say from experience that we can use tools like PSSE and then publish results for dynamic stability into other formats. So you can convert from one to the other and then back again. Isn't that right, Chris?
Yeah, PSSE and PSLF have very similar models. The format's a little different from the DYR and DYD files, but they're very similar, and I think it's pretty easy to build one from the other. TSAT actually uses either. I think it uses either format to create its model. I don't think it has its own extension. I think it uses PSSE or PSLF files.
So we have a question in from Cindy. So can models created in ETAP be imported to TSAT or the other dynamic modeling software such as PSSE and PSLF?
We haven't experienced trying to do that. It might be possible with certain tools, but it's just not something we've dealt with. And I think it would be very hard to create one and have it be very accurate just because the data formats, and usually ETAP models are usually a whole site of, let's say, 50 inverters all modeled. I don't know how it would create the equivalent for you. So it might be possible, but it's not something we've actually worked with. Have you heard of that, Ian?
Yeah, so we use ETAP. We're very familiar with that tool. It's one of the more common medium and low voltage tools. Really good for arc flash for those that have some experience with that. However, like even ETAP uses some kind of weird workarounds when it comes to modeling inverters, and it's a little challenging sometimes to get the right data out of ETAP, both for short circuit data and for low flow power flow data. So I think just trying to convert it would be challenging on its face just because of the incompatibility of ETAP working with the type of data and analysis that PSSE and PSLF are doing. Now, I think it can be a good resource for gathering data. For example, if you have a built ETAP model that has transformer impedance data, cable impedance data, back to earlier in the discussion, all that data is critical for building this PSSE model, but I don't believe there's an easy conversion from ETAP or other tools that are like that, like Easy Power or SKM to get into PSSE, whether it's for dynamics or not. And again, if anybody knows more about it, we'd be happy to discuss that at more length. But I don't think we've seen much movement on that particular front with the data conversion.
Yeah, if ETAP was the actual record model of the site, and it was, if everyone agreed that it was correct, it could definitely be used to create a PSSE model. I'm just not aware of a automatic conversion.
Yeah, and when you talk about model conversion, I do know of one that does work really, really well. So it's APA, formerly CAPE, so, short circuit software. It's a common transmission level short circuit program that's used for I don't know, most say about half the utilities in the US use just Aspen or Cape, and Cape's that one. So Cape and PSSE are both owned by Siemens, and even before that was the case, Cape had a lot of tools to convert their models into PSSE formats that then you could then convert into a PSSE transient stability model as well. Matter of fact, I think that tool also that program also had tools to kind of work back and forth for doing transient stability analysis and then pushing it back in for short circuit impacts to relaying and system the system operation studies that you're going to look at. Basically, they call it system simulator in there. So I think there are tools where there is some conversion capabilities, but I think it's limited. I think there's only a few that do that well. For example, if you had an Aspen file, you could probably turn that into a DXT, import it into Cape, and then convert it over to PSSE. It'd be complicated, but possible.
Yeah. Well, another thing to keep in mind, anytime you do a conversion like that, no matter how good the tool is, and we've worked with some of them, you're going to lose a little bit every time in the conversion, and every step needs a person looking at it to make sure it's right. And if you convert it 3 times, it's probably going to be unrecognizable.
Yeah, that's a good point. So regardless, if you're going to use these conversion tools, it might help speed things up, but absolutely, you have to check that model. And I wouldn't trust it until we went through it pretty carefully to make sure that we don't have bad data that's throwing off our results. Sometimes it's evident, sometimes the devil's in the details, and it can be very challenging to sort that out. So, but definitely a thought. Christopher has a question. Are there any resources for newer engineers to dynamic models that would help in learning how to model and create these studies?
I don't know of any specific resources, but I think most software manufacturers, they'll have their own classes on how to do it. I think, yeah, I'm sure Siemens they have classes all over the country for PSSE. I'm pretty sure TSAT does. Probably all the other software tools too, like ETAP and Aspen and Cape. I think probably going to the manufacturer and asking them the easiest way to learn is probably the way I would go.
Yeah, a couple things too. So we mentioned earlier that there's guides coming out from MISO and ERCOT that have very specific guidelines for how these models have to be created and tested.
That's true.
So that would be a great place to start. Also, learning by doing, sometimes just getting into it, getting your hands dirty, working with the software and trying to do that, even if it was on your own time, like a learning project. If you were to have the software, like Chris mentions, maybe you take some training on how to use that software to do this dynamic stability modeling, and then try to recreate a model that meets the requirements of ERCOT. That's essentially the process. It isn't trivial. There's a fair amount of work involved to get there, but that would be a great learning experience on how to do this on your own, especially if you were interested and willing to learn.
I know for PSSE and ERCOT, there's actually a tool that a lot of people use to create the dynamic models and studies, and I think you have to create the model yourself, but it'll actually run through and automatically test a lot of the stuff. I don't have a lot of experience in it, but I know it exists, and I played with it a little, and it seemed to work pretty good on their test site. Whether it works on a real site, it probably does, or ERCOT wouldn't be. And I think they're actually pushing it a little bit. Last I looked, it only worked with PSSE 35, but it's possible they've updated it to 36 by now. If I can think of the name of that, I'll let you know. I can't think of it off the top of my head.
You actually you kind of shine a light on maybe one more point I'd like to make is, especially with that PSSE tool, they release different versions, and I believe they just released a new version here this last week or so. Make sure that you understand the version that your requirements are in for the utility. A lot of times utilities will lock into an older version, so they're not constantly updating, and they can standardize, and they'll do a big update maybe every 5 years or something like that. So make sure you pay attention to that. Using a much older or a very new version of PSSE could potentially be a pitfall for your project.
Yeah. PSSE, it seems like most people that use PSSE have kind of standardized on PSSE 34 and then more recently shifted to 35, but it doesn't seem like 36 has really had much takeoff yet for dynamic studies. And a lot of the dynamic models are specific to one version, especially if it's like a user-defined model and not a standard model. It won't work in another version if you get it for one.
Yeah, I think the recent release I was mentioning is PSSE 36.4.0 is what just came out. So, but you're right. I mean, there's kind of like industry acceptance or maybe utility acceptance on a certain version. So make sure that you pay attention to that. That's a critical thing that can be a misstep. Other question. So from Benjamin, what do you look for to know if the base DYR file received from an inverter manufacturer is of good quality or bad quality?
There's not really any one indicator. You might be able to look at it and notice some things that are out of place, especially if it's for a conventional one and the parameters that from the generator don't match the parameters in the dynamic file. It's probably a problem, but I think the biggest way you find out that it's not good is you just test it and see what the response is. And if it doesn't behave well, it's not good. It's hard to, I'm sure there's somebody that can look at them and see that this is going to be a problem, but I don't know anybody like that. I think you got to just run it and see how it responds.
Yeah, one of my thoughts might be is, for example, if we're talking conventional generator, you should be able to check that DYR against the conventional generator spec sheet, and they should line up pretty close. There may be a few parameters that are changed, and if they're changed, they should be to reasonable values that do make logical sense. You should be able to sort all that out. Usually when we see bad models, you see incomplete models, models with garbage data, or just placeholder values that really don't make any sense, to Chris's point. So I think that there are some low-hanging fruit to find out whether you have a quality model or not. But I would also say that expertise is critical here, and having somebody that is very familiar with this is going to be a much better indicator of success than just looking at a file on a space and without having that experience.
Yeah, and because dynamics build on the steady state model, a lot of the time it's the steady state parameters that are causing a problem. If it doesn't solve cleanly in the steady state model, like if you get one of the line parameters wrong, it's going to use 10 times the number of R's to push power through that it should. The dynamics are going to be pretty ugly too. So
Yeah.
Creating that site model and getting that accurate from accurate data, it matters a lot. So you need both pieces, and a lot of it, figuring out what's wrong when it's not working, like Ian said, is a lot of just expertise and knowing what to look for.
All right.
The more you
Another
do, the better
question
you do
here
at it.
from William. Have you worked on any islanded or off-grid sites? And what does an islanded site need that is different from a conventional grid connection for dynamic stability?
We haven't done a ton of that, but we have a little bit. We recently did, believe it was a data center that was connected to just a lot of conventional generators, and they're trying to run it entirely off the generation. And it was tricky to get it working. I think most of the things that it was a large enough site, most of the things it needs are similar to what you'd need for a grid connected one. It's just a lot different modeling it because there's no large utility that's providing all that spinning inertia. I'm trying to think of what else it needed that was that much different. You worked on that a little bit too, Ian. What did you think?
Yeah, so I think that without that source, the system is always going to be a bit weaker than normal. So you're going to see bigger fluctuations in stability when you have less, you don't have the system. Essentially, when you have a disturbance on a very strong system with a lot of generators, all the generators do a little bit. Where you have a islanded system where maybe you have one or two generators, and generally your generators are not grossly oversized. Usually you have about as much generation as you need. Maybe with some margin, maybe you have, like a 2 times margin on your generation. But that generation has to do a lot when it sees fault. It has to do all the work. So I think what you see is when you have like islanded or off-grid sites and you have these dynamic swings, that they're much more pronounced and sometimes can be very challenging to overcome.
Yeah, and I think one of the biggest things I noticed modeling it, not so much from the outside perspective, but just modeling it, you have to be everything has to be a little higher quality because there's not a large slack of generation that can fix it. If you have a problem, you have to fix it yourself with your own generators, and if they're not behaving, you do see it a lot more.
Yeah. Well, I think that's it for questions. I wanted to really thank everybody for attending today. I really appreciate the time to speak with you on this topic. I think this is going to be a hot topic going forward in the industry, especially with the way that we're seeing these requirements really kind of amp up across the entire industry. So hopefully this was enlightening. If you have any other questions, please feel to reach out. And thank you much for your time.
Yeah, thank you everyone for showing up.